Okay, so the last thing we discussed, by my recollection, is this right here, talking about indicators and the importance of choosing the right indicators for a particular type of acid-base titration. Okay, so let me talk about solubility equilibria. And what we were talking about in this section, we'll be talking about ionic compounds, which we would typically consider to be insoluble, all right? In truth and in fact, every ionic compound has a degree of solubility in water. Now, some would be greater, for example, sodium chloride or potassium nitrate. Those are virtually always soluble in water. And then you have compounds like silver chloride, which is very sparingly soluble in water. And that will be the focus of our discussion today. So if you take silver chloride and add it to water, eventually you're going to have an equilibrium that takes place because of the sparingly solubility of silver chloride. Only a small amount of ions will end up in solution, all right? So eventually you're going to have this equilibrium taking place, and we can write down an equilibrium expression for this particular situation, and that is this right here. And the equilibrium constant in this case is called the solubility product, symbolized by KSP, right? So KSP is the solubility product constant, and this only applies to what I said before, those ionic compounds that are sparingly soluble. Another example would be magnesium fluoride. You see that when it dissociates, it forms those ions, and therefore this would be the KSP expression for magnesium fluoride. If you look at silver carbonate, we can write down a KSP for that particular system, as you can see here, all right? If you look at calcium phosphate, then the KSP expression is seen here. And what you can see in each of these cases is that KSP will be equal to the concentration of the ions in the solution raised to the power, which would be their coefficients in the balanced equation for the dissociation, all right? So when you have an ionic compound that is dissolving in a solution, or that is dissolved in a solution, the Q value, or more specifically QSP, must be less than KSP, right? So basically we're talking about an unsaturated solution in that particular situation. Now, in that case, you will not see any solid, right? So no precipitate will be formed in that particular situation. Now, if Q is equal to KSP, then that would be a saturated solution, right? And then if Q is greater than KSP, then that would be a supersaturated solution, which would be very unstable. And therefore, what you'll observe in that case is a precipitate, right? So basically, if you add two ions together that would normally form an ionic compound, the value of the QSP must be greater than KSP in order for the precipitate to form. Otherwise, you will not get a precipitate, all right? So what you'll find is that the KSP values are relatively small. After all, we're talking about, as I said before, ionic compounds, which are sparingly soluble. And this table here gives you some examples. And if you look at these values, you see that they're very small. In fact, the largest value that I can identify here is this one right here, 2.4 times 10 to the minus 4, which is a very small number in and of itself. But as you can see, you can get even much smaller numbers like bismuth sulfide, 1.6 times 10 to the minus 72. So basically, KSP values are typically very small numbers, all right? And also, let me show you where in Canvas it is. There is a table that I've posted in Canvas, which gives you a more comprehensive list of ionic compounds, which you will have access to during your exams. So let me go to tables. And then where it says solubility product constants. So this is the table that you will have access to. It gives you the formula, the name, and the corresponding KSP values. All right. And again, you can see typically very small numbers. All right. So this is the table that you'll have access to doing your tests, exams, etc. All right. So let me go back to the PowerPoint. Okay. So typically when it comes to calculations involving solubility, they usually come in two forms. One is where you're asked to determine the solubility. And let me talk about the difference first between molar solubility and solubility. So the molar solubility is expressed in moles per liters, or M, and that is the number of moles of the solute dissolved in a liter of solution and liter of saturated solution, very important. And then the solubility, which is normally expressed in grams per liter, is the number of grams of solute dissolved in 1 liter of a saturated solution. So basically, molar solubility can be converted to solubility by multiplying by the molar mass. And you can do the reverse to get from solubility to molar solubility. So some problems will be of a form which you can solve using either one of these two flowcharts, right? So for example, if you're given the solubility of a compound, you can find the molar solubility by dividing by the molar mass, and then you can go from here based on the equation for the dissociation, determine the concentrations of the ions and the anions, and then based on that, you can plug those numbers into the KSP expression to get the KSP value. And then there's also the possibility of you being given a KSP value, and you can do the reverse to get the solubility of the compound. So you can go from KSP to get the concentration of the anions and cations, again, using the balanced equation for the dissociation. And then from here to here, you can find the molar solubility by multiplying by the, or by dividing by the molar mass. And then, well, actually, by looking at the stoichiometry of the balanced equation. And then from here to here, you can divide the molar solubility or multiply the molar solubility by the molar mass, and that will give you the mass, or I should say the solubility of the compound in grams per liter. All right. So just to illustrate how to do a problem of this type, this question says, what is the solubility of silver chloride in grams per liter? So the equation for the dissociation of silver chloride is given here, and the KSP value is given here, right? So what I would do is I would set up an ice table. Black ink, that's what I prefer. Okay, so the ice table, initial values would be no silver ions, no chloride ions, and then the change here, I'm going to say the change is plus S, where S is the molar solubility. Molar solubility. All right? So basically what that means is that S represents the amount or the concentration of the silver chloride that goes into solution, which means that the change in the concentration of silver ions would be plus S. And because of the 1-to-1 mole ratio between the silver ions and the chloride ions, that would be plus S as well. So at equilibrium, you're going to have S and S here, right? Now, KSP would be equal to the concentration of Ag plus times the concentration of Cl minus, right? So basically, we're going to plug these values or these terms into where we have these concentration values. So that would be S times S, which would be equal to S squared, which means that S would be equal to the square root of KSP, which would be equal to square root of 1.6 times 10 to the minus 10. So if I were to do that number crunching on my calculator, (1.6) times 10 to the minus 10, I would get 1.3 times 10 to the minus 5 M, right? But that's a molar solubility. The question is asking for the solubility in grams per liter. So basically, we need to take the 1.3 times 10 to the minus 5 moles per liter, and multiply that by the molar mass, which will be up here, and 1 mole down here. So the molar mass of silver is, I can't see it from here. The molar mass of silver is 107.9. And then I'll add to that molar mass of chlorine, which is 35.45. And according to my calculations, this works out to be equal to 143.35. Okay, where did it fall to? I heard it drop. Oh, there it is. Okay, so 143.35 will go here. 143.35 grams. So I multiply that by 1.3 times 10 to the minus 10. And according to my calculations, this works out to be equal to 1.86 times 10 to the minus 8 grams per liter, right? And of course, this comes as no surprise because silver chloride is sparingly soluble in water. So therefore, that would be the concentration or the solubility of silver chloride expressed in grams per liter. All right. Any questions about this particular example? Any questions? Any questions? Okay, so let me just skip all this here. Okay, seems as if there's some contradiction between what I got and what the PowerPoint says. Let me see here. Oh, wait a minute. 1.3 times 10 to the minus 5 multiplied by 143.35. Okay, so this should be to the minus 3. Okay, so please make a note of that. Not minus 8, minus 3, which is still a small number. All right. Okay, so let's get out of this here. And this is just giving you a small sample of different sparingly soluble ionic compounds and their KSP expressions. So we did this one earlier, right? The KSP expression is concentration of silver ions times the concentration of Cl minus. And as far as the solubility is concerned, because of the 1-to-1 ratio, S would be the solubility of the silver ions, S would be the solubility of the chloride anions, and when we put them into the KSP expression, you end up with KSP is equal to S squared. That's what we saw in the previous example. And if we were to find S, S would be equal to the square root of KSP in that case. In the case of barium sulfate, very similar because, again, of the 1-to-1 ratio between the barium and sulfate. However, in the case of silver carbonate, the equation for that dissociation is Ag2CO3 dissociating to form 2Ag plus CO3 2 minus. So in this case here, the change here will be plus 2S, and the change here would be S, right? Which is what we have here and here, right? 2S for the silver anion, the silver cations, and S would be the solubility or the change in concentration for the carbonate ions. And therefore, when you plug these expressions into the KSP is equal to concentration of Ag plus squared times the concentration of CO3 2 minus. When we plug these terms into their respective positions here and here, you're going to end up with KSP is equal to 4S cubed, and therefore S will be equal to, and I see there's a kind of typo here. This should be a parentheses here and here. So S will be equal to KSP divided by 4 raised to the power 1/3 or cube rooted, all right? And so on and so forth for the others. You can probably figure those out by yourself, all right? Okay, so that's the relationship between KSP and molar solubility. All right, so here is a question which says, if 2.0 mils of a 0.200 m sodium hydroxide are added to 1.00 liter of a 0.100 m calcium chloride solution, will a precipitate form, all right? Now, the ions that will be present in the solution are these right here. The sodium, the hydroxide, the calcium, and the chloride. Now, of these ions, the combination that would potentially give you a precipitate would be the calcium and the hydroxide, right? Because calcium chloride is soluble in water, sodium hydroxide is soluble in water, so therefore, and sodium chloride is definitely soluble in water. So therefore, what we should look at is this equilibrium here, the equilibrium of CaOH2, which would dissociate to form Ca2 plus 2OH minus. 2, oh Lord. 2OH minus, all right? And what we'd have to do is look up the KSP value for calcium hydroxide. So let me see if I can find it in a previous slide. I think it should be, okay, calcium hydroxide, calcium hydroxide, according to this, the KSP value is 8.0 times 10 to the minus 6. So okay, so KSP is equal to 8.0 times 10 to the minus 6, all right? Okay, now the thing is that we need to find out what the concentration of calcium and hydroxide will be upon mixing, all right? And then we calculate the QSP based on that. And if QSP is less than the KSP, then no precipitate will form. But if QSP is greater than KSP, then a precipitate would form. Okay, so what we need to do first is find the concentration of hydroxides, right? And that would be based on information provided here. We are adding 2 mils of 0.200 m sodium hydroxide to 1.0 liters of calcium chloride. So basically, we're going to use the C1V1 equal to C2V2 equation, right? What we're trying to find is C2 for calcium hydroxide upon mixing. So that would be equal to C1V1 over V2. C1 would be the initial concentration of the sodium hydroxide, which is 0.200 m, times V1, which is the initial volume, which is 2.00 milliliters. And the final volume would be the 2 milliliters. Something here. Okay, the final volume is going to be the sum of, where's this thing be? Okay. The sum of the 2 milliliters here and the 1.00 liters here, right? So 2 milliliters is the same as 0.002 liters. So basically, or that would be equal to hold on, wait a minute. 0.002. So that would be equal to 1020 milliliters, right? Because what I did was add 2 milliliters to 1 liter. 1 liter or 1.0 liter is the same thing as 1,000 milliliters. So I've added 1,000 milliliters to 2 mils. So that would actually be 1,002. Let me erase this here. That should be 1,002 milliliters. All right, so 1,002 milliliters. So let's see what that gives. That gives 0.2 times 2 divided by 1,002. So according to my calculation, this works out to equal to 3.99 times 10 to the minus 4 m. And then I do a similar calculation for the calcium ions. that would be equal to the initial concentration, which is 0.100 m, multiplied by 1,000 mils, divided by the final volume, which is again going to be 1,002 milliliters. And let's see what that gives. 0.1 times 1,000 divided by 1,002. So according to my calculations, this works out to be equal to 0.0998. And this would be M. So KSP, or I should say QSP, upon mixing, would be equal to the concentration of calcium times the concentration of hydroxide upon mixing. So that would be equal to, for calcium, 0.0998 multiplied by the concentration of hydroxide, which is 3.99 times 10 to the minus 4 squared. Okay, so let's see what that gives. 3.99 times 10 to the minus 4 squared multiplied by 0.998. So according to my calculation, this works out to be equal to 1.59 times 10 to the minus 7, right? Now, if you compare this value, which is the QSP, to the KSP, what do we notice? The QSP is less than the KSP. So therefore, no precipitate will be formed. All right? And that's how you do that. Okay, any questions about this one?
Can I ask why the OH is squared?
Because you have a 2 here.
Oh.
All right?
That's
Well, it comes from the balance equation upon dissociation of the calcium hydroxide. So when the calcium hydroxide dissociates, it produces 1 mole of calcium and 2 moles of hydroxide for every 1 mole of calcium hydroxide that dissociates. Okay, any other questions? Any other questions? Any other questions? Okay, so let me scroll down. Okay, now here's an interesting question. This is a method of separating ions when you have 2 present, both of them present in a solution. So this question says, what concentration of silver is required to precipitate only silver bromide in a solution that contains Br minus and Cl minus at a concentration of 0.002 m, all right? So what we have here is a solution containing both bromide and chloride ions, and you're using silver ions to precipitate selectively the bromide ions from the solution. So basically, you have to determine what level of concentration of silver that you need in order to effect that precipitation without removing any of the chloride ions present. They're both at the same concentration, by the way. Both the bromide and the chloride ions are both at the concentration of 0.02 m, right? So basically, because we are asked to precipitate only silver bromide, that seems to suggest that the silver bromide would be less soluble compared to the silver chloride. And you can look at that, you can actually determine that from their KSP values. So what we'll be focusing on firstly is the dissociation of the silver bromide. And here's a KSP value for that dissociation. And the KSP expression, of course, is concentration of silver ions times the concentration of bromide ions. That product is equal to KSP, right? Which means that the concentration of silver that you're going to need at the very least to precipitate the silver bromide would be given by this equation, which is simply a rearrangement of this. And then all we have to do now is plug in the numbers for both KSP and the concentration of the bromide, and you're going to end up with 3.9 times 10 to the minus 11 m. Now, please note that this represents the concentration at the saturation point. In other words, you won't have a precipitate formed yet, right? So that is basically the floor in terms of the lowest concentration of silver ions before precipitation. Well, actually, it's the highest concentration of silver ions before precipitation will take place. Then we look at the dissociation of the silver chloride, and we write down a similar, well, we find out the KSP for that from the tables, and we write down a similar expression for KSP, and then we rearrange, just like we did here, for the concentration of Ag+, which would be equal to KSP divided by the concentration of the chloride. And then we put the numbers in, and then we get 8.0 times 10 to the minus 9. What that represents is the highest concentration of silver ions that you can have before you have the precipitation of the chloride ions, all right? So therefore, it says what concentration of silver is required? Well, the concentration of silver required would be greater than 3.9 times 10 to the minus 11 and less than 8 times 10 to the minus 9. So therefore, this is the answer. The concentration of Ag+ is between the ranges, or within this range, from a low of 3.9 times 10 to the minus 11. That's the highest you can get until precipitation occurs. And then the high point here is where the concentration of silver ions would have to be less than before any chloride ions are precipitated. So the term we use to describe this process, we call this selective precipitation. Selective precipitation. And it is used to separate ions, precipitation. It is used to separate a mixture of ions when you have both ions, or probably more than two ions, present in a solution. You add a precipitant. That's what the silver ions is called in this particular situation. It's called a precipitant. You use it to selectively remove one, and the other remains in a solution. Okay, any questions about this example? Any questions? All right. We talked about the common ion effect earlier with respect to dissociation of weak acids. We can apply the same principle to the type of compounds we were just talking about, the sparingly soluble ionic compounds, all right? And what you'll find is that just as how the common ion depresses the dissociation of weak acids, the common ion, in the case of sparingly soluble ionic compounds, will depress their dissociation. And as a result, will depress their solubility, right? So to illustrate this, we're going to look at the molar solubility of silver bromide in pure water and then in a 0.0010 M solution of sodium bromide, right? So this is the equilibrium for silver bromide. I'm going to start off with pure water, right? So I'm going to start off with an ice table, right? Initially, you'd have no silver ions and no bromide ions. And let's say the solubility is S, so that means that the change in concentration of silver ions would be plus S, and the same is true here. And therefore, the concentration of silver ions would be S and S right here. KSP, therefore, is going to be equal to the concentration of Ag+ times the concentration of Br-, and we're going to put S and S here. So therefore, this will be equal to S squared, and therefore S will be equal to the square root of KSP, and the KSP of silver bromide is 7.7 times 10 to the minus 13. So here I'm going to put square root of 7.7 times 10 to the minus 13, all right? So let's find the square root of that. 7.7 times 10 to the minus 13. And then I find the square root of that. So according to my calculations, this works out to be equal to 8.8 times 10 to the minus 7 M. All right, so that would be the molar solubility of silver bromide in pure water. So what I'm going to do, because I'm going to need a space, I'm going to write down this answer here, which is the answer for A, right? Because what we're going to do is make a comparison between the solubility of silver bromide in pure water and the solubility of silver bromide in 0.0010 m sodium bromide. Okay, now, as we said before, this is the equilibrium for the dissociation of silver bromide. Let me just erase some things under here. In the case of sodium bromide, because sodium bromide is completely soluble in water, what will happen is that NaBr will dissociate completely to form Na plus Br minus, right? Now, in this particular case, initially, things will be a bit different compared to what we just saw in the case of pure water, because now we're dissolving the silver bromide in this right here, which means that the initial concentration of the bromide ion will come from the sodium bromide, which is 0.0010 m, right? So instead of just 0 here in the case of pure water, because there's bromide ions, the initial concentration of bromide is going to be 0.0010 m, all right? The change is going to be plus S again and plus S here. So therefore, at equilibrium, you're going to have S here, and here, you're going to have S plus 0.0010 m. Now, what you can do here is you can make an approximation to make life easier for you. And the approximation is that S is so small compared to 0.0010 that this would be approximately equal to 0.0010 m. In other words, S is almost 0, in other words, right? So let me erase some stuff from this side here. So the result of that would be, when you plug it into the KSP expression, is that you're going to end up with the silver ion concentration would be S, and the bromide ion concentration would be 0.0010 m. And that would still be equal to KSP. What was the KSP again? Can somebody remind me? The KSP for silver bromide. Okay, right. So basically, this is all you have to solve. So therefore, S will be equal to 7.7 times 10 to the minus 13 divided by 0.0010 m. Well, we don't need the m because 10 to the minus 13 divided by 0.0010. So according to my calculation, this works out to be equal to 7.7 times 10 to the minus 10 m, all right? So this would be the solubility of silver bromide in the presence of 0.0010 m sodium bromide. So let me write that number here, 7.7 times 10 to the minus 10 m. So if you compare this number to this value right here, you see that the solubility of silver bromide decreases as a result of being, well, when you try to dissolve it in 0.0010 m sodium bromide. So this is another example of the common ion effect, right? In this case, the common ion is the bromide ion. The presence of the bromide ion basically pushes the equilibrium in that direction, right? And therefore, as a result, it reduces the solubility of silver bromide, all right? And you can see that clearly by the numbers that are shown there. Okay, any questions about this example? Any questions? And that goes for you guys out there in Zoom as well. If you have any questions, feel free to ask. Okay. Let's see what's next. Let's get rid of all this. Okay, so what we're going to look at in this particular section is the relationship between, oh, I keep forgetting to get rid of this thing right here. Okay, so another thing that affects the solubility of some sparingly soluble salts is the pH of the solution, right? And again, this is related to some degree related to the common ion effect and also related to Le Chatelier's principle. So as stated here, the presence of common ion decreases the solubility. That's what we just discovered in the previous slide, right? What you'll find is that when it comes to sparingly soluble bases, they will dissolve in acidic solutions, and insoluble acids will dissolve basic solutions, all right? So what we're going to look at now is the example of magnesium hydroxide. When added to water, it dissociates to form, of course, magnesium and hydroxide ions, and I think there's a Kp value given, right? 1.2 times 10 to the minus 12, all right? Now, we can rearrange this equation, or we can not rearrange, but determine the solubility expression as it relates to the Ksp value, and that would be equal to, ultimately equal to 4s cubed, right? And therefore, S would be equal to, when you solve for S, 1.4 times 10 to the minus 4, all right? So that would be the solubility of magnesium hydroxide in pure water, right? Now, as far as the hydroxide ion concentration is concerned, that would be equal to twice the solubility based on the stoichiometry here. So therefore, the concentration of hydroxide is equal to 2.8 times 10 to the minus 4. And based on that, we can find the pH, right? Of course, you have to find the pOH first, right? Which is minus log the concentration of OH minus. And then you subtract that value from 14, and that gives you the pH, right? So this would be the pH of the solution that results from this dissociation in pure water, all right? Now, if the pH is less than 10.45, right? In other words, let's say you add acid and the pH is decreased to some value less than 10.45. What that means basically is that the concentration of the hydroxide ion would decrease because you're making it more acidic. The acid will add to the hydroxide ions to form water, which means that the equilibrium will shift to the right. So this is the reaction that I just described. When you add acid, it will react with the hydroxide ions, and therefore the equilibrium will shift to the right, and therefore the solubility of the magnesium hydroxide would increase, all right? So you can understand this based on Le Chatelier's principle. You add acid, it decreases the concentration of the hydroxide ions, the equilibrium will shift to form more hydroxide ions to the right, and therefore, as a result, the solubility of the magnesium hydroxide increases. And of course, the opposite will be true if the pH is greater than 10.45. In other words, if you add more base to the solution, you're increasing the concentration of the hydroxide ions, and therefore, you're pushing the equilibrium to the left, which means that you are favoring the formation of magnesium hydroxide, which means that the solubility of magnesium hydroxide will decrease, all right? So this shows you how the pH of the solution will affect the solubility of certain sparingly soluble bases, basically, all right? Okay, so should I talk about this? What time is it? Okay, let me talk about this now. Let's talk about complex ions. Now, a complex ion is basically a metal ion surrounded by either neutral molecules or anions, all right? And a good example of this would be this complex ion formed as a result of the cobalt 2+ combining with 4 chloride ions to form this complex ion right here, all right? Now, one thing about complex ions is, well, for one, it's an equilibrium system, and therefore we can write down an equilibrium expression for the complex ion formation. So in this particular case, the equilibrium constant is equal to the concentration of the complex ion divided by the product of the concentration of the cobalt 2+ and the chloride ions raised to the 4th power. And the equilibrium constant for these complexes, we call them the formation constant or stability constant. And the stability constant is one term that is probably more applicable because what you'll find is that these complex ions are very stable, and the Kf value, the stability constant or formation constant, reflects that, because typically what you'll find is that the Kf value is very high, and the higher the Kf value, the greater would be the stability of the complex. And I think and this is just showing you the difference between the cobalt 2+ ion in terms of the color. And then when you add the chloride ions, it forms a blue solution. So this is blue and this is pink. Now, these are just some examples of complex ions. These are their equilibrium equations. And if you look at these values, you see that these are very high values, right? 1.5 times 10 to, so this is basically 15 million. And this is 2 million. I think that's the lowest value among these here. So you see that these values are very high. And what they do is reflect the stability of the complex, right? The more stable the complex, the more the equilibrium will favor these ions, and the lower would be the concentration of the silver ions, and in this case, the ammonia molecules as well. And this is just basically giving you some an example of what I mentioned before, selective precipitation. You can selectively, if you let's say, for example, you have a mixture of all these ions in one beaker or test tube, you can add certain reagents to selectively precipitate some of these. So if you want to precipitate silver, mercury 1, lead 2, and bismuth 3, well, not bismuth 3, but up to lead 2, you can add HCl, and these are the complexes formed, and these are their KSP values, and so on and so forth for the others, all right? And again, this is something akin to what we just mentioned just now, more in the form of a flowchart, where, again, you can selectively remove certain cations by just adding the right reagent, which would allow for the precipitation of those ions. This is just some mention about flame tests. I don't know if you have done this before, but basically you can use these tests to determine the presence of certain ions. Basically what you do is take nichrome wire, which is an alloy of nickel and chromium, which does not burn, and you dip it in your solution containing the ion, and then you put it in a flame, and the different colors basically indicate the type of ions in the solution. So like this kind of pinkish red flame is due to lithium, the yellow flame here is for sodium, and so on and so forth. And this is just basically talking about some of these reactions in biological systems, how an eggshell is formed. Eggshell is basically calcium carbonate formed as a result of calcium and carbonate coming together to form that solid. Now, there's an enzyme known as carbonic anhydrase, which basically takes the carbon dioxide and water from the atmosphere to form carbonic acid. And then carbonic acid will undergo 2 dissociations to form the carbonate. And that carbonate will combine with calcium to form the calcium carbonate, which makes up the eggshell. And that's basically it for this chapter. All right, now what I'm going to do now is go to the assignment. Now, I think we started assignment number 5, right? And I realized this morning I was looking over I was looking over the assignments, and I realized that I did not include questions dealing with complex ion formation. So I added 2 more questions to that assignment. Let me see if I can bring it up here. So please, you may need to download it again, or if you want to, well, download that page. I think it's only 2 pages I've added. Let me see here. So I added, okay, so I added question number 9 and 10, right? So please make a note of that. So let me scroll up to, now, did I do any of these questions with you guys? Did I go through? I'm sorry? Oh, I never gave you the assignment. Oh, hold on. I thought that.
You mentioned it last time, but then you didn't.
Oh, okay. All right. I forgot to print it. Okay. All right. Let me choose some of the more challenging ones to help you with. I think you should be able to do number 1, because number 1 is basically the straight application of Henderson-Hasselbalch equation. So what I'm going to do is jump to question number 2, which says, what is the pH of each solution, A, B, and C, after titrating 12.00 mils of 0.0500 m sodium hydroxide? So basically, you're starting off with 12.00 mils of 0.0500 m sodium hydroxide, and then you're adding different volumes of different acid solutions. In the case of A, you're adding 6.00 mils of 0.200 m benzoic acid, and it gives you the Ka value for benzoic acid. Okay, so let me, you know what? Let me see if I can copy this here and paste it onto. Okay, let's see here. Oh gosh, I can't paste it onto this. Okay, let me try Word. Okay, let's see if this works. No, it doesn't work. Shoot. All right. Oh, did work. Okay. So here is okay. So it says, what is the pH of each solution, A, B, and C, after titrating with 12.00 mils of sodium hydroxide, 0.0500 m sodium hydroxide, and you're adding, in the case of A, 6.00 mils of 0.20 m benzoic acid, and it gives you the Ka for the acid, which is 6.28 times 10 to the minus 5. Okay, so the first thing I would do is I would find the number of moles of each of them, right? So in the case of the sodium hydroxide, I'd find the number of moles. They gave us the volume and they gave us the molarity, right? So the number of moles of NaOH would be equal to 12.00 mils, which we have to convert to liters. So 1 liter over 1,000 mils. And then I'll multiply that by the molarity, which is 0.0500 moles per liter. Let's see what that gives. And folks, again, please do these calculations along with me because I could be wrong. So I got 6.00 times 10 to the minus 4 moles. All right? So that's for sodium hydroxide. And I'm going to do the same calculation for the benzoic acid. Now, since I'm lazy, I'm just going to use HA for benzoic acid, right? So that would be equal to 6.00 mils, again converted to liters. So you're going to have 1 liter over 1,000 mils times the molarity, which is, in the case of benzoic acid, 0.200 m or moles per liter. And according to my calculation, that's 6 times 10 to the minus 3 times 0.2. So according to my calculations, this works out to be 1.2 times 10 to the minus 3 moles, all right? The next thing I would do is write down the balanced equation for the reaction between the sodium hydroxide and the benzoic acid. And of course, the product of that reaction is sodium benzoate plus water, right? And then what I would do next is, write down an ice table for this reaction. So initially, you're going to have 6.00 times 10 to the minus 4 moles for the sodium hydroxide, For the acid, you're going to have 1.2. Let me draw a line here to distinguish between those two. 1.2 times 10 to the minus 3 moles. And then for the sodium salt of the acid, you would have none initially, right? Now, remember now, this is an acid-base reaction. The reaction will go in one direction. In other words, no equilibrium will occur, which means that one of these two will be used up completely. In other words, the limiting reactant will be used up. So of those two, the sodium hydroxide or the sodium benzoate, which one, based on the mole values in each case, which one would be the limiting reactant?
Sodium hydroxide.
Sodium hydroxide, exactly. So therefore, we're going to say minus 6.00 times 10 to the minus 4 moles of the sodium hydroxide will react. And because of the 1-to-1 mole ratio between those two, minus 6.00 times 10 to the minus 4 moles of the acid will react. And again, because of the 1-to-1 mole ratio, as far as the sodium salt is concerned, plus 6.00 times 10 to the minus 4 moles of the sodium salt will be produced. All right? Okay, so at the end of the reaction, when the reaction is complete, you're going to have no sodium hydroxide. You're going to have 6.00 times 10 to the minus 4 moles of the acid. And here you're going to have 6.00 times 10 to the minus 4 moles of the salt, right? Now, the next thing I'm going to do is find the concentration of the acid. And because, well, before we do that, and let me just squeeze that into this box right here, we need to find the total volume. What's the total volume when you mix 12 mils of the sodium hydroxide to 6 mils of the base? So that would be 12.00 mils plus 6.00 mils. That would be equal to 18.00 mils, right? So the next step is to find the concentration of A minus, which, by the way, would be equal to the concentration of HA, right? And the reason why I know that is because the mole values are the same, and the volume would be the same because they're both in the same solution, right? So we can kill two birds with one stone. The concentration of A minus is the same thing as the concentration of HA, which is 6.00 times 10 to the minus 4 moles divided by 18.00 mils, and then we convert that to liters. So that would be 1 liter over 1,000 mils. And whatever that gives, that would be the answer. So let me do that calculation. 6 times 10 to the minus 4 divided by 1/8 E3 minus. Okay, so according to my calculations, this works out to be equal to 0.0333 M. Okay, so here we have a solution of a weak acid and its conjugate base. So what do we call that combination? We call that a what? What do we call a solution which contains a weak acid and the conjugate base of that acid? We just learned that term.
Buffer solution.
Buffer solution, thank you. And how do we calculate the pH of a buffer solution? What equation do we use to calculate the pH of a buffer solution? pH is equal to what? pKa plus log concentration of the conjugate base over the concentration of the acid. Very good. Now, because we know that the concentration of the conjugate base and the acid are the same, guess what? These two will cancel out. So we're going to end up with log of 1. Now, what's log of 1? Nope. 0. So therefore, that means that the pH in this case is going to be equal to the pKa, right? Which would be minus log of the Ka value, which was given in the question. What was it again? Let me scroll up. 6.28 times 10 to the minus 5. So minus log of 6.28 times 10 to the minus 5. So let me do that calculation, 6.28 times 10 to the minus 5. Log of that. So according to my calculation, that would be 4.202. And that would be the answer for the A part of that question. All right? Any questions about this one? Any questions? Any questions? No questions? Okay. How much time do we have left? Okay, I think we can do the B part at least. Okay, so let me go back to the question. So in the case of the B part, actually, hold on, let me see. Basically, all right, you know what? I can skip the B part because if you understand what we did in the A part, the B part is very similar. The only difference is that it's a different acid, and therefore the Ka value is different, right? Everything else, the volume is the same, right? So everything else would be the same. The only difference would be the type of acid. So let's scroll down to the C part. Let's see what the C part has to offer. Oh, the C part, same thing. Oh, no, the concentration is different. Okay, so let's work on the C part here. So let me copy this part here and go back to the Word document. Okay, so what I'm going to do is I'm going to paste this here, and I'm going to get rid of this, all this crap here. Okay, so we're starting off with the same sodium hydroxide, 12 mils of the 0.0500 M, but this time now we're working with a different acid and a different molarity, all right? So let's see what that would give in this case. The approach will be similar, but of course, there'll be some differences because of the different numbers involved, all right? So, okay, so again, just like we did before, we're gonna find the number of moles of the sodium hydroxide, which is going to be the same. I don't think I need to do that calculation. What did I get for that? Can you remind me? Okay, so we did that calculation already. Don't need to repeat it. Now, in the case of the butanoic acid, I'm going to use HA again. That would be equal to 6.00 mils. We convert that to liters, which is 1 liter over 1,000 mils. And then we multiply by the molarity, which is 0.100 M. Okay, so let's see what that gives. So 6 times 10 to the minus 3 times 0.1. Okay, so in this case here, we're going to have 6.00 times 10 to the minus 4 moles, all right? So we do the same thing as before. We write down the balance equation for the reaction. Sodium hydroxide plus the acid gives you NaA plus H2O. So initially, we're going to have 6.00 times 10 to the minus 4 moles of the sodium hydroxide. We're going to have the same mole value for the acid. And we're going to have none of this. We don't need to worry about the water. Now, in this case here, both of these will be limiting because both of them are the same value. So we're going to say the change for the sodium hydroxide is minus 6.00 times 10 to the minus 4 moles. Same thing here. And then on this side, you're going to have plus 6.00 times 10 to the minus 4 moles. And at the end of the reaction, you're going to have 0 here, 0 here, and here you're going to have 6.00 times 10 to the minus 4 moles, right? So the next thing we need to do is calculate the molarity. To do that, we need the total volume. Total volume would be equal to what? 6.00 mils plus 6.00 mils, which would be equal to 12.00 mils. And then the next step is the molarity. Now, there's only one species for which we can calculate the molarity because we have 0 for the acid, 0 for the sodium hydroxide. So the molarity of the NaA, which is the same thing as molarity of the A minus, would be equal to the mole value, which is 6.00 times 10 to the minus 4 moles, divided by the 12.00 mils, which we have to convert to liters, 1 liter over 1,000 mils. So let's see what that gives. So that's 6 times 10 to the minus 4 divided by 12. Okay, so according to my calculations, I'm going to end up with the molarity being equal to 0.05. How many sig figs? 3 sig figs, 0.0 m. All right. So that would be the molarity of the A minus, the conjugate base of the acid. So how do we determine the pH of that? Well, what we need to do is set up another ice table, because this time what we have to look at is what happens when the A minus interacts with the water. So the equation for that reaction is the A minus plus H2O. And the key thing you need to remember here is that the A minus is acting as a base. So therefore, you're going to end up with HA plus OH minus, right? So initially, you're going to have 0.050 for the molarity of the A minus. You're going to have none of this and none of this. The change here is going to be minus X because we don't know, it's a weak base. We don't know how much of it will dissociate. So we're going to say that X represents the amount of A minus that reacts, which means that according to the stoichiometry, the change in HA would be plus X, and the change in the OH minus would be plus X as well. So at the equilibrium stage, you're going to have 0.050 minus X. Here we're going to have X. Here we're going to have X. Now, this is acting as a base. So what we can write down here is a Kb expression for the A minus. We're undergoing the hydrolysis. That would be equal to the concentration of HA times the concentration of OH minus divided by the concentration of A minus at equilibrium, all right? Now, we can make an approximation here that X is small compared to 0.050. So we can say that this is approximately equal to 0.050. So when we plug these values into this equation, you're going to end up with X times X over 0.050, which will be equal to X squared over 0.050. Now, actually 2 zeros. That's equal to Kb. But the question now arises, what is Kb? Because Kb would be for the A minus, but you will not be able to find Kb in any table in most tables for this particular conjugate base. However, the question did give us the Ka for the acid, right? So how would you find Kb? Anybody? They gave us Ka is equal to 1.52 times 10 to the minus 5. So that's a Ka for the acid. So how would you find the Kb for the conjugate base? Anybody? What's the relationship between the Ka, excuse me, what's the relationship between the Ka of an acid and the Kb for its conjugate base. Okay, multiply Ka times Kb gives you what? Kw, exactly. So therefore, we can say that Kb will be equal to Kw divided by Ka, which in this case is going to be equal to x squared over 0.500. And therefore, this implies that x will be equal to the square root of Kw divided by Ka times 0.500. So x will be equal to the square root of 1.00 times 10 to the minus 14, which is Kw, divided by the Ka, which is, what was it again? 1.52 times 10 to the minus 5. 1.52 times 10 to the minus 5, multiplied by 0.0500, right? So that is how we calculate x. So let me do that calculation. 1 times 10 to the minus 14, multiplied by 0.05, divided by 1.52 times 10 to the minus 5, and then find the square root of that. Okay, so according to my calculation, this works out to be equal to 5.73 times 10 to the minus 6, all right? But we're not finished yet, because remember the question is asking for the pH, right? What we have calculated so far is x. And what is x equal to based on the second ice table here? X is equal to the concentration of HA, but it's also equal to the concentration of OH minus. So we can set this to be equal to the concentration of OH minus. So from here, how do we find the pH? Now that we know what the concentration of the hydroxide ion is, how do we find the pH? Okay, so basically because pH plus pOH is equal to 14.00, as Erin just correctly said, to find the pH, that would be equal to 14.00 minus the pOH, which is, well, actually, there's one step we skipped. It should be minus the minus log of the OH minus, which is 5.73 times 10 to the minus 6, all right? So that works out. So let me work this out. So the 5.73 times 10 to the minus 6, I find the log of that. And then subtract that from 14. Oh, shoot. Okay, 5.73. So this works out to be equal to 8.76. And that would be the pH of that solution. Okay, so that's basically how that is done. So you can attempt the rest of the questions, which brings me to assignment number 4. Did I give you a deadline date for that?
No.
Okay, so you can turn in assignment number 4 tomorrow. If you have any questions about it, you know, if you have any difficulty with it, I'll be available today during my office hours from 3:30 to 7:30 this evening. So feel free to call me or come by my office if you have any questions about doing assignment number 4. So now you should be able to also complete number 5. In fact, let me see if I can put a deadline to that one. Knowing me, I'll forget to do so. So let me do so now. So for assignment number 5, okay, for assignment number 5, I'll let that be due on the 1st, which is Friday coming. All right. So I've just opened up a Dropbox for that one. All right, folks, so that's it for today. I'll see you guys on Wednesday.